Okay, so we're now in chapter 6, which is not process scheduling, it's process synchronization. It's a mistake here in the slide. Slideshow. And we're going to talk about the critical section problem. That's one thing. Synchronization means that see here it says classic problems of synchronization. Peterson's solution, you're gonna have to know that for the exam. Critical section problem. Synchronization means that the processes are synchronized. They work, they don't conflict with one another. They work together properly. So, for example, they don't step on each other's toes, let's say like that. That's an example in metaphoric English. For example, if one is writing to memory, the other one shouldn't be writing to the exact same location. Or if he is, I should know about it. Like he shouldn't be writing at the same time. So let's go straight to this. Remember, we're going to think about processes running concurrently, even though we may have only one processor. And we really have, let's say, round robin, and we have time slices. So really, they're not running at the exact same moment. But for our purposes, they are running at the same moment. Because remember, the operating system is going to stop one and start the other anytime and give me the feeling that they're both running at the same time. So even though they're not running at the same time, on a theoretical basis, they are. For example, so there's such a thing as the consumer-producer problem. This is an important idea we're going to talk about. What is the producer-consumer problem? Well, just think about it like a person making, donuts and somebody eating the donuts. So I'm the producer of the donuts and you're the consumer of the donuts. What don't you want to happen? Two things you don't want to happen. But two things shouldn't happen.
You shouldn't eat everything.
You shouldn't eat everything and I try to eat and I just eat the plate and there's nothing there. And what's the other problem? I shouldn't produce more than the plate can hold. The plate has a finite size. I don't want to fill my whole restaurant with donuts. That's the one thing I miss from America, actually. Dunkin' Donuts. They actually had Dunkin' Donuts here at one point, like a long time ago. Anyway, I don't want to produce too many, and I don't want to produce too few. That's basically it. So here, let's read what it says here. Illustration of the problem. Suppose that we wanted to, what's the point of the producer-consumer? I'm a different person from the producer. There's two processes. That's the mashal of donuts. Let's talk about it in computers. I am a process consuming data, and you're a process producer. Can you think of an example? Can anybody think of an example of a producer-consumer situation in computers that they've encountered?
It's like running out of hardware space.
No, not really. Running out of hardware space. Yeah, okay, that's similar. No, that's not the example I want.
Maybe a loop going through file, like going through data.
Go through data?
Like a loop that's like running through, let's say, an array of data or whatever, a database even. And like there's a different process that's like putting information about, I don't know, people into this database.
Oh, okay, right.
And the process is taking that information and doing something.
And he's reading from an array, and there's somebody writing to the array, and I'm like doing something to the array, but now he hasn't written, the array is empty, and I read it as zeros, and I sort of try to do something with zeros. But I was actually thinking of an example you might have seen. For example, let's say you're watching a movie. I don't know if you guys watch movies, but you're watching a movie on your computer and it stutters, right? Or there's a lag, some kind of lag. That's a producer-consumer problem. There's somebody doing some digital signal processing. He's reading data and producing a visual, and the visual is consuming it to present to you at a certain speed. By the way, when you do think about that, that's also kind of real time. I have to calculate the new image to put on at the rate of the movie. If I do it slower, then it's going to not be good. If I do it too fast, I have to do it at the right rate. So there's a consumer, the producer is the digital signal processor that's reading the file, and the producer is like this displayer. I mean, they're both parts of the program. The displayer is displaying it on the screen. He's trying to display the next thing and he doesn't have it. Or, even in Zoom, any kind of delay that you have in Zoom is I'm trying to consume it at a certain speed and he's not producing it at the right speed. So let's read what he wrote here. Suppose that we wanted to provide a solution to the consumer-producer problem that fills all buffers. Oh, because he introduced it and I didn't show it to you. The buffers so that, fine. We can do this by having an integer counter that keeps track of the number of full buffers. Initially, the counter is set to 0. It is incremented by the producer after it produces a new buffer. It is decremented by the consumer after it consumes a new buffer. Well, all right, I don't want to deal with this, but set to 0 is incremented by the producer after it produces a new buffer and is decremented by the consumer. Right. Now, if you have a number, if it's 0, then you don't try to consume. If you have a number that says there's 0 donuts on the plate, and every time I put something there, I put a donut, I increment the number by 1, 2, 3, 4, 5 until it gets to 10. And I have a limit of 10. And now when I come to eat, I first check, is the number greater than 0? If it is, then I take a donut, I reduce the number by 1. So the consumer is reducing the number by 1, and the producer is incrementing it by 1. That's the basic idea of controlling it, so that I don't try to consume when there isn't anything there. I have this number that I check. So here, let's look at this program. Let's look at this program. What do? I say, while true, so I have this infinite loop, and I say, while counter is equal, who am I? I'm the producer. Very important, I'm the producer. So I'm producing, I don't want to produce when don't I produce? When the plate is full. So if the counter equals buffer size, my counter is reached 10, my buffer size is 10. So then look at this semicolon here. That means I'm in an infinite loop, right? I never go out of this. That is my loop. It's like braces, semicolon. I'm just here. This is, of course, this is very bad. This is a concept also we need to know, which is called a busy wait. This is called, I'm waiting here, right? I'm just waiting, but I'm busy because I'm in a loop, constantly checking. Is counter equal to, yes, it is. Check again, is it equal? Yes, it is. I'm constantly checking. Now, how could this, when would I ever get out of this loop? I'm never changing counter. How would I ever get out of this loop?
The consumer changes counter.
What?
The consumer changes counter.
Right, exactly. There's two processes. And this variable counter is shared. It's like a global. It's more than a global, super global. Why is it more than a global? A global is between the different functions in my process. This is a super global. It's between two different processes. It's shared between two different processes. So the consumer may eat a donut and lower the number down to 9. And then it's no longer, and then I'm going to break out of the loop. But this is called a busy wait. So write that down, busy wait. Busy wait means I'm burning the CPU. I'm using the CPU just to wait around, just to do nothing. I'm making that loop. That loop is taking up CPU. But this is a solution. It's just because it's busy wait doesn't mean it's not a good solution, but it's a solution. So let's look at this. So now if I got out of this loop, what must have been happened? Tell me your name again. Leora. What Leora said, the consumer changed counter, brought it down to 8, let's say, 4. So now what am I going to do? I also have a pointer in the buffer. This is a little bit of mathematical wizardry here, but like in is where in the buffer I want to put my next donut, right? It's not a plate. It's really a tray with marked off places. It's an array. So where in that tray do I put the next donut? I'm going to put it in the in place, which is going to be a number from 0 to, buffer size -1. So 0 to 9, let's say. Now, what's going to happen is like this. I'm going to increment it. N equals n plus 1. but not quite incrementing, because when I get to 9, I don't want to go to 10. Where do I want to go after 9? I want to try to put, the next place I'm going to try to put my donut is in place 0. I went from 0, 1, 2, 3. I got up to 9, and now all of a sudden it tells me the counter is less. The counter went down to 8. There's a space there. Where's the space going to be? Well, he's eating always in order. So if I just put in, if I was just, the last place I put was 9, he must have eaten from the beginning. He didn't eat where I just ate. He ate, you know, first in, first out. So he ate that first one. So the next place I want to go is 0. If there's a missing spot, it's going to be in 0. How do I get to 0 from 9? The answer is I go to 10, but do modulo of the size. 10 modulo 10 will give me 0. So that's what this is. So I say like this: take my 9, add to it 1, I get 10. Modulo 10, if that's the size of my buffer, gives me 0. So in is actually 0. So the next time around, basically I put here in a 9, then I went to 10, but the next time around I'll actually put in will be 0, and I'll know to put it in 0. Now the in here is not shared. Is it not shared? Right, this in here is not shared because the consumer could have consumed 6 donuts at once, right? I don't know the rate of his consumption. The point of the producer-consumer problem is that the rates of production and consumption are varying. They're not, and we need to synchronize them. That's why our chapter is called Process Synchronization. The production of donuts could be faster than the consumption, or the consumption could be faster than the production. We don't know. But we want to synchronize. We want to make sure that the production never is too great and consumption never tries to consume when there isn't something there to consume. So next time I come, I'll now come, if counter is at buffer, that means he only ate 1. I managed to get 1 more donut in, and then I went to the next place, and now counter again is buffer size, so he only ate 1. So now I'm going to wait here, wait here, wait here. Now all of a sudden he eats 5. I'm going to put it into in, put a donut into in, right? Next produce. Whatever I produce, I'm going to put here, and then I'm going to increment, and counter is going to go up. Why does counter go up? Because that's the count of how many I have. Yeah.
How is there room in the buffer in?
How is there room in the buffer to put?
Yeah, like in the in spot.
Well, I don't know. Notice they use like a define here, buffer size. I made a buffer of whatever size. I'm just saying 10, but somebody made an array of 10 spaces. And if it filled up, the point is what I want to do is I want to fill it up. And then when I get to the end, if it's got extra space, I want to start filling it from the other side.
How do you know it's the last spot that's empty?
How do I know?
That it's the last spot that's empty.
Because I know something about the consumer. I know that the consumer eats from 0 up to 9. Now, he doesn't start random. He doesn't eat at random places. He eats at 0, 1, 2, 3. It could be that he just ate 7. And if he just ate 7, and I'm at 9, then I'm still going to put it at 1. And there'll be a gap here. And then he'll eat 8, 9, and then he'll come back to 0, whatever. Yeah. But
So why are you putting in the last spot on the first spot?
here?
Yeah.
No, well, let's take an example. Let's take a different example. Let's say that in is, I was explaining n. Let's say in is 5. And the whole buffer is full. The whole buffer is full. It is 5. Now, when he eats, he could be anywhere. I don't know that he's at 1, actually. Well, that's a good question. Where is he eating? Maybe you're right. Maybe in is shared, and maybe in he knows to eat. Let's see the producer. Let's see the producer. Yeah, here, the consumer doesn't have in. He is out. Okay, let's look at the consumer. Let's see more detail about what we're doing here. So again, the consumer is in a busy wait. Here they put the colon here, semicolon. Here the consumer is in a busy wait as long as counter is 0. That means there's no donuts on the table. Now if he broke out of this loop, it must be because counter went up. Who made the counter go up? Over here, the producer made the counter go up when he produced something. So again, we're imagining if the whole thing is empty, you see, the whole thing could be empty. In is where I am in the array. Counter is how much stuff there is. I could be at any location in the array. Wait, where's that marker? Sorry for those of you at home. So in could be here. Let's say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh. So in could be here. And the producer said, in is 4. So he's going to put the donut over here. Here's the donut. And now we have to decide what's the case. Is it all full or not full? If it's not full, then count, he's going to make count go up by 1. So let's say it was empty. So count is now going to equal 1. And he's going to get to his loop again. And the count is not equal to buffer size. Buffer size is 10. So he's going to put in, it also went up by 1. In goes to here now, right? That's in equals in plus 1. Modulo buffer size. Well, if it was 4, it's now 5. 5 modulo 10 is still 5. So in is now here. He's going to put a donut here. And he's going to, let's just say he ran the gamut. And he put in donuts everywhere because count was small. But eventually count got to be 10 or 9, I don't know, whatever, 10. Count got to be 10. Well, where is in now?
Place 3.
In is here? I'll take your word for it. In is there. Count is 10. What?
It's at 4.
What?
It is at 4, I think.
Well, that's the thing. I didn't think about it. If in was at 4,
If you just put in 3, then it would be at 4.
if I put in 1, yeah, I think in is at 4. I agree with you. Because I'm at 4. In is here. As if when I started here and I said, and in was at 4, and I said, and count was at 0. So count went to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I stopped. And I didn't put it in. I didn't put it in. So in is here. Good. In is here. Now where's out? I have no idea where out is. Wait. No. Here is out. Out could be anywhere. Out is wherever he was from the last time he ate.
But if in and out are not lined up.
Out could be here.
So then you're putting it at 4 though.
So let's wait a second. Let's say the minute he eats, does he do counter minus minus?
Yeah.
Yeah, here. Oh, it's a little bit bad slide. Counter minus minus. So if counter was at counter, while counter is at 0, do nothing. But counter's not at 0, so he's going to consume a whole lot now. Because counter, he's going to make counter go up. So he was here, so he's going to consume. Let's say that he consumed to here, but in the meantime, you're saying.
In is not lined up with out.
Right. How does he know? Count went down. He's going to try to put another donut here.
Right.
Problem. You're right. It's a problem. That's synchronization. So what if out is here? Also, so this is not right. You're right. This is a problem. Yeah. Because in and out are not lined up.
Can you explain the problem again?
Yeah. Well, wherever I put out, let's say I put out here. And this is the situation. Now, there's nothing to stop out from starting to consume, right? So he'll consume this one, and then out will go here. And then out will go here. And he'll start consuming. Well, I guess he can't be here. The problem was that if, let's say, out consumes something, and that's the situation, now the counter has gone down to 8, and the producer will want to produce, but he's here. He's not here. He's going to produce in the wrong location. That's the problem. Let's think about it again. What about if we say like this? In and out, they for sure start off at the same location, right? That we're going to agree. Let's say the beginning of time 0, the beginning of creation. So what's going to happen first? Well, count is 0, so the consumer won't consume anything, and the producer will produce something, right? And maybe he'll produce a lot. Let's say he produces to here, and in is now here. Maybe he could produce more, but it's taking him time to produce for some reason. Now, out is here. He sees that count is not 0. He starts consuming. So he eats this one, and he eats this one, and he eats this one. He's here now. Yeah? Now, you tell me what happens. Either the consumer takes another one, or he starts producing. Well, if he starts producing, what's he going to produce? He's going to produce over here, and he'll keep going. Maybe he'll stop. Maybe he'll stop. Let's say he stops. For whatever reason, it took him time. So in is now over here. In is now over here because he produced that one. He moved to here, and he stopped because he wasn't ready yet to do anything. Out will start consuming. And you see what I'm saying? If you notice, there's no way that out will ever get past in.
So I have to start at the same place.
Yes. In other words, the example I gave was an impossible situation where I said, let's just say arbitrarily that in is here and out is there. Then we'll have problems. But if we start at time 0, we'll see that the consumer, which is out, will never get past him. Yeah? Consumer now could consume. Eventually, if he consumes everything here, he'll stop here, and he'll be here again, and we're back to where we were. And if he stops over here, let's say the consumer stopped here, he ate these ones, and then this one he for some reason didn't need to eat yet. So now the producer can start producing. He might produce, 2, and he's here now. So it'll still work. He can produce more. He'll never get past. So it is a good solution. Of course, we're done. We'll stop here. But the main thing I don't like about, well, there's going to be 2 things we're going to see that next time there's a problem with it. One is that we don't like this busy wait. That's very bad. And the other is that there can be problems with this counter minus minus. There can be problems that the counter minus minus and the counter plus plus happen simultaneously in such a way that we have an indeterminate result. And that's our real problem. Okay, we'll stop there.
Thank you.
Well, actually, we had a break.
Yeah.